Hi Mindsetters, great to be with you. I'm John and I'm really excited about this show. Now, there are a couple of little technical issues, there are strikes on the go, and unfortunately that's why we don't have a social media person, but we're watching the page. We've got people in the background that aren't on screen, and I will check the Facebook page during the break as well. So welcome to Learn Extra. Grade 12s, we're doing a really important section. Last week when I was with you, we spoke about diffraction. Hope you remembered that, because this week we're going to carry it on. Now, guys, I know there's a lot happening, but put all the other stuff aside and let's get into some physical science. This week, we are going to be talking about interference. Now, if you can imagine, if I have a garbled message coming to you, and 1 minute I'm talking about future stars, and the next minute I'm talking about science, you're going to get a confused message. When other things distract you, we say that's interference. When you are trying to study, and somebody comes and says, poke, poke, can't you come to the movies? There are all sorts of distractions. They're interfering with what you're doing. Don't interfere. I want to focus on what I'm doing. Okay, so interference, distraction. That's what the common word means. But guys, it's not like that in science. Interference has a very special meaning. And we're going to investigate that. We're going to have a look and make sure that we understand what interference is all about. So let's get to it. Let's see what we're going to do in this lesson. We've got quite a lot to get through, so I want to just make sure that you are very clear with what's going on. So the first thing that we're going to do is we're going to revise this word interference. We're going to revise the different types of interference, constructive and destructive interference of waves. Very important. We're also going to take a look at a demonstration of interference of waves. It's a simulation. We won't be able to look at this in real life, and we'll see during the show if we can get that interference demonstration up and working. And then the next part we're going to do is we're going to explain the diffraction pattern, which we spoke about last time when light passes through a single slit by using Huygens principle and interference. And the last section we're going to look at, you need to understand this, is Young's double slit experiment. We'll take all of that together and then apply it to some past or previous exam paper questions. So guys, we've got a lot to do. Let's get straight into it. Let's make sure that we stay on track. So the first thing that I'm going to say is, well, what is interference? It's not your brother bugging you or your sister playing loud music. That isn't interference. But there is a practical example that you might have seen at home. If you've got the TV on and your mom in the kitchen turns on the beaters, the cake mixer, and it makes a really loud sound, you might have seen on the TV screen, it kind of goes snowy and wavy, and we say, what's happening? There's interference. There's interference because of electromagnetic radiation or electromagnetic waves. The waves that are being produced by the motor of the mixer are interfering with the TV waves that are coming in as a signal. And so you're getting a distorted or an interfered signal. That's what we're saying interference is. That's an example of interference. But what is it really? So we've got to recognize, we've got to have a short definition of interference. Interference is what happens when waves from different sources move through the same medium and undergo superposition. And then continue as they were. So if I had to draw a little diagram to illustrate this, we'll come to the word superposition. What we would recognize, I'm going to draw a little diagram, and let's try and explain it. So we'll use a blank piece of page right down at the bottom to just sketch a little bit there. I didn't leave myself enough space. So let's say that's a little wave, and we've got another little wave that's coming towards it. And you can now see what will happen. If they're moving in the same medium, and this one is moving towards this one, what's going to happen when they overlap? So if that one overlaps like that, what's going to happen? Well, there's going to have to be, they're overlapping, they're in the same medium. So the particles in the orange wave are all wanting to move down. The orange particles are wanting to move down. The pink particles in this region, they're also wanting to move down. So when both of them are moving down, what do you think is going to happen? Well, in this section where they've overlapped and they're in the same region, what's going to happen is quite obvious. We're going to get a bigger trough. We're going to get something that is bigger than either of the first two. Okay? You got that. They were at the same space, they overlapped, and we added them together. So that's exactly what the principle of superposition says, is that when waves interfere, we can apply the principle of superposition. Depending on how they interfere, we can add the amplitudes together. So that was one example. I hope you can see that you get a bigger wave than what we started. And because it's bigger, has a larger amplitude, A is larger, then we say that this is an example of constructive interference. A stands for amplitude, and I've illustrated that. But guys, that's not the only example. We need to be very clear. What else could happen? Let me take my little pieces apart from each other. I'm just going to select them again, move that one that way, and I'm going to change this one altogether and make sure that we've got a different scenario. So I'm just going to delete that one. I'm going to delete it altogether, take this away, and throw it away for the moment. I'm going to say, let's take my little wave over here. Let's draw another one. This time, I'm going to draw my pink wave this way around. Now, what do you notice when the pink one moves towards the orange one? Pink one moving towards the orange one moves towards the pink one. Can you see something here? They're overlapping, but they're not in the same way. So these particles, the ones at the crest here, those particles were all wanting to move upwards. The one, because the wave is moving from left to right, this orange wave is moving in this direction. These particles are on the way up. These particles on this side of the orange trough, they're on the way down. When they overlap, they're going to pull each other in different directions. They're not going to be happy. The one wants to go up, the other one wants to go down. What are we going to get? We're going to get cancelling out. So if this had the pink one had an amplitude, let's say the pink amplitude was 2 centimeters, and the orange amplitude was 2 centimeters, but this one was in the opposite direction, we make that minus. When you add 2 centimeters plus minus 2 centimeters, you're going to get 0 centimeters. So for the time that they're overlapping, that they're moving through each other, there's going to be a cancelling out. We don't say cancelling out, we say destructive interference. In fact, what we can recognize as destructive interference is when the amplitude is less, the final amplitude of the new wave. The white one, as I drew earlier, the new wave, amplitude new, is going to be less than the amplitude of either that one or the pink one. So as long as the amplitude is less than either of those, then we can say that it's destructive interference. It doesn't have to be 0 to be destructive. Please get that very clear. So make sure that you've got that sorted out. Destructive, when there's cancelling out, the end result is less than either of the two. The bigger one is going to be smaller than the biggest one than when you started. Final point on this interference story is please notice something, that if I had the wave there and it was moving in that direction to the left, after superposition, it would continue moving in its own direction, and that one would continue moving in its own direction. So they would move through each other, and at the point when they're moving through each other, we get interference, then they move apart, and they carry on as normal. Got it? Hope so. Right. Let's just make sure that I filled in everything here so that we've described it. Principle of superposition, I'm just going to summarize this by simply saying you add the amplitudes. But make sure of the signs. When we talk about constructive interference, then the result is going to be bigger, is larger than before, than before. So we add together. So it's amplitude nu is equal to amplitude 1 plus amplitude 2, and it's going to be bigger. Make sure that you understand this very clearly. Guys, the important thing here for our discussion tonight is you need to understand that when you get a crest meeting a crest or a trough overlapping with another trough, then you're going to get constructive interference. When things move through the same position and they meet in the same phase, when they're in phase with each other, then you're going to get constructive interference. When they meet and they're out of phase, then you're going to get destructive interference. So make sure that you've got that clear. I want to just delete this, and we just throw that away. Destructive interference, it's going to happen where you get a crest overlapping with a trough. What we say is when there's the two waves, the waves are out of phase. Then you're going to get destructive interference. The amplitude of the new wave will be less than either A1 or A2. We're applying the principle of superposition. Hope you've got that very clear, and so that you understand that this is a very important principle that we need to apply. Okay, so we've covered that. I want to go on to my next slide, and I'm just going to brief this. I'm not going to be able to do it in the time before the ad break. I'm going to read through it, and we're going to talk it through to start with. I want you to see if you can work out some of the answers. So what it's talking about here is about light and interference of light. It says monochromatic red light passes through a double slit, as shown in the diagram below. Circular wavefronts advancing towards the screen are shown between the slits, and the screen as dotted lines and solid lines. The solid lines represent crests, and the dotted lines represent troughs. What we're going to say now is interference of circular wavefronts results in an interference pattern observed on the screen. So P, Q, and R represent centers of different bands of interference patterns. And here we go. Here's the pattern. You've got monochromatic light moving in that direction, two slits, and here we've got dotted and solid lines. I'm going to try and highlight the solid lines in one color, and the dotted lines will then stand out. So those are the solid lines, and the dotted lines are the in-between ones. So remember what it said? The solid lines are the crests. So all these ones are crests, and the dotted ones, the dotted white ones, are troughs. Okay, here are the questions. What type of interference takes place at point A? Now, point A is over here. Point A is over there. And I hope you can see that is where you've got two dotted lines overlapping. So you've got two dotted lines overlapping. See if you can work that out. We haven't even done Young's experiment, but we're answering this question because it deals with the basics of interference. And then it says, is the band P a dark band or a red band? And explain because of the interference. So there you go. Have a quick look at the question. It does come from the November 2010 exam paper. See if you can answer it. We'll come back to this later in the show. I want you to see if you can answer it and post your questions or your answers on Facebook. We'll pick up and see who's giving us an answer. So the answer is, what type of interference is at point A, and is band P a dark or a color? I think that we're about time to go to a break. So let's take that break now. Make sure you stay in touch with us, and I'll be checking Facebook right while you're going for your break. Hi guys, welcome back, and it's great to have you with us on this Learn Extra Grade 12 show where we're looking at interference. And of course, we have to say thank you to Macmillan for making this show possible. Really great to have you all online. I've just been checking the Facebook page, and I want to pick up on something. One of the learners has posted a question. Not sure that I fully understand what they're asking, but let me try and answer it. They said to me, in the question that we asked, in this question, where does monochromatic red light come from? So we're looking at that phrase, monochromatic red light. So what do we understand by the word monochromatic? That's the first thing. Monochromatic. And we must break it down. Mono simply means one, and chromatic, chromo means color. And so we're saying that this is light of one color. One color of light is one frequency or one band of frequencies that are close together. So it's one frequency. And if you want to know where monochromatic red light comes from, well, here's an example. I'll just step out and I'll shine it on my arm here. I've got a little laser pointer here. It's not doing me any harm, but it's showing you what monochromatic red light looks from. It comes from a laser. The source of those waves are all in phase. They're in the same frequency, and they are moving through the medium at the same rate. There is another word that comes with this respect that I want to just mention. We sometimes talk about them as being coherent sources. So this relates to frequency. Monochromatic relates to frequency. Coherent relates to the phase. So we can have waves of the same frequency, but they could be totally out of phase. That's not going to help us. We want them to be of the same frequency and in phase. Now, while you were away, I want to just mention one other thing in terms of this phase story and the idea of interference, constructive and destructive. I want to give you an example, and let's do it like this. Let's say here's position A and here's a position B. Let's pretend that these two positions are sources of waves. Let's say that they're producing waves that both travel in the same direction. So they're both traveling from left to right. What we're going to do is let's also assume that they produce the same frequency. Now, I'm not very good at drawing waves, but I'm going to try and draw them more or less at the same frequency, something like that. What I want you to count is the number of wavelengths. And we say that would be one wavelength, that would be two wavelengths, that would be three wavelengths, that would be four wavelengths. Let's just cut that off at 4 wavelengths. I'm going to just shade that out. I'm now going to say to you, if we started the second wave, the second source was producing waves, and it produced waves of the same frequency in the same direction, can you see that if they reach this point over here, the same point over here, and they were entering the same medium, even if they weren't exactly in line with each other, where they met, they would be a whole number of wavelengths. 1, 2, 3 wavelengths. So here, this is a wavelength, this is another wavelength, and that's a third wavelength. Whereas this one was 1, 2, 3, 4 wavelengths. The one was 3 wavelengths, the other was 4 wavelengths in total. But they were a whole number of wavelengths. If they met different lengths of path, but they lent at one whole wavelength into that same medium, and they collided, at that point, superposition was to take place, then what type of interference would take place? What we'd need to recognize is if they did that at whole numbers of wavelengths, 4 and 3, then they would be in phase. They'd be undergoing constructive interference. Constructive interference. But the question now becomes, what would happen if they weren't one whole wavelength apart? Let's say, for example, it was only, I'm going to move it to try and illustrate this. I'm going to move it. It's no longer 3. I'm going to change it and make it a different number of wavelengths. Let's say that it's now going to be 2.5 wavelengths apart. So if I do that, I move all of that so that they're now in that position. So when this one is coming up, this one at the bottom is not. It's half a wavelength out. The difference is no longer a full wavelength. Let me just tidy this up so you can see it. That's 1, 2, and there's a half wavelength here. This is only half a wavelength. They're in a different position. This particle at this point wants to start going up, where this particle is want to start going down. This particle is going to want to go up. Wavelengths are moving apart. At this point, because they're not a whole wavelength apart, they're half a wavelength apart, a number times a half wavelength apart, they're going to undergo destructive interference. There's going to be cancelling out. So, principle for you to understand, when waves move together and they're a certain distance apart, they're moving at the same speed, and they collide with each other, and they happen to reach the point, the distance from the source to the point of intersection is a whole number of wavelengths, constructive interference. If it's a distance and it's not a whole number of wavelengths, destructive interference. Guys, that's an extremely important principle for you to understand. We're going to need it to explain some of the phenomena that we're going to investigate in today's lesson. And so, talking about those phenomena, let's move straight on to that very principle. Remember last weekend, Tuesday afternoon, Tuesday evening, we were talking about diffraction. We said diffraction is the bending of light behind a barrier, and we found that diffraction took place in water waves, bent behind barriers. We also said diffraction can take place with sound, it can take place with light. The evidence for diffraction taking place with light is a very famous experiment called the single slit experiment. It was first discovered by Fresnel and a long time ago, 1800s, somewhere around there. Let me just remind you exactly what that's about. We said if we've got some wave fronts, these are wave fronts, and they're moving towards a barrier. So this orange thing here is a barrier, and there's a slit in the barrier. There's a gap, a slit. What we said is that you can recognize that there's going to be a pattern. Light is going to pass through this barrier, which might have a symbol A, that slit with a width of A. Then it's going to produce a strange sort of pattern. And I've redrawn it over here for you to try and explain it. Think about this. If light was going to go straight through the barrier, then the majority of the light would go through and it would form a central bright band. And that's exactly what I've got here. This is a screen, which I've shown over there at the bottom, that this light is projected onto. And we're looking at from the top over here on this section. This is the top view, but now we're looking from the side view onto the screen. We're saying to ourselves, what's going to happen? The light will pass through the barrier, it's going to pass through the slit, and it's going to form mostly a bright band here. It's very bright, and because it was monochromatic red light, it will form a red band, a bright red band. But what we notice next is next to the band is a dark region. There's a fringe. This little region here is a black or place where there's no, it's dark. There's no light. There's no light. No red light. Okay? Then what you should notice is the second band. The second band is narrow and it's not as bright. It's a dim red band. Dim red. And then there's another big black band, dark band, and then a very thin red band. Now, guys, this is the interference or the diffraction pattern for a single slit. Sometimes you get pictures like this one. There are other diagrams that I want to show you how they can represent this so that you don't get confused when you see it. I'm going to just draw it at the top here because I've tried to illustrate this as this is the brightest band here. And it's big and broad. It's bright. And then it gets dimmer and so on. So what we sometimes see in books is they draw intensity lines. And they say it goes like that, then it goes like that, then there's a big bright one, and then a little one, and oh, I didn't draw that one low enough, so let me draw this part a bit better so that you can see it. So there's the straight bit, and there's the one, and then it gets smaller and smaller. This one is the widest, and it's the brightest. This is about intensity, bright. This one is small, and it's dim. And between them, where it touches the horizontal axis, that are points of destructive interference. There is no light. And so I've given it away. We explain this pattern by explaining that light is undergoing constructive and destructive interference. You can say, where is it coming from? Where are the sources? Well, let's go and have a look at it. Right down at the bottom, I mentioned to you earlier that you're going to have to use Huygens principle. Do you remember what Huygens principle said? Huygens principle said that on any wave front, we can represent them as a number of different point sources. So that white dot over here, that white dot, let me just highlight it in pink, that little dot is a source of waves, circular little waves. In the slit, I've just magnified the gap to make it big. Now, guys, here's the important thing. These point sources are going to allow light to travel through with the same frequency, the same speed. So if they're going straight, the distance, I want to draw a straight white line, the distance from here to here, and the distance from here to here, and the distance from this point source to that point source, and from that point source to that point source, can you see that those parallel lines of light, these parallel lines, are going to move through the same distance? The distance is the same, which means that the wavelengths are going to be the same, which means the number of wavelengths are going to be the same. So when they get to here, they're going to be in phase. We're going to see them combining, and there's going to be constructive interference. Constructive interference. So when they travel the same distance, the same number of wavelengths in that distance, constructive. And what do you expect when there's constructive interference? Very bright light, big broad band, the same width as the slit, and sometimes a little bit bigger because it's going to spill over. Now, how do we explain the dark band? I'm going to exaggerate it a little bit. And so I'm going to take some of these lines and I'm going to say to ourselves, okay, let's remove these lines. And we're going to say from the top of that band, from that source to that source over there, to that position over there, or let me just do two. I'm going to do that one to that one. I'm going to take these ones away. Like that. I'm going to say this one that was coming from that source and this one that was coming from that source, when they land up in the same point, I want to move it. It's not letting me. Let me just delete it and redraw it. Here we go. We just put this one in from there to there. Hope you can see that the top line, this line here, is going to be slightly longer. This distance is a longer distance. This one is not as long. So this one is shorter. The difference in the distances between the top and the bottom could be about half a wavelength. And if it's half a wavelength, what's going to happen when they coincide? We're going to get destructive interference. When they're not a whole number of wavelengths apart, you're going to get destructive interference. When light interferes destructively, you're going to see nothing. It's going to go black. That's why you get a bright band, then a dark band, and then a slightly dimmer band. Why is the dimmer band there? Well, again, the point is here that what you've got to recognize is that the light traveling from these point sources is not, some of them are going to interfere constructively, some of them are going to interfere destructively. They're not all going to be constructive. And so that's why they get smaller and dimmer and the bands get further and further apart. Okay, guys, I hope that's making sense. We were going to look at this principle or this problem of single slit diffraction last week. We didn't have time to explain it, but it fits in so nicely with interference. That's why I've left it over as well. So when you look at a single slit interference pattern or diffraction pattern, you need to remember the principle is the bright band is because of constructive interference. Dark band, destructive interference. I hope you've got that. The last thing that I just want to mention on this, remember the relationship that we've got. We recognize that the sine of the angle of diffraction is equal to lambda times m, the number of bands divided by a. So the sine of the angle of diffraction, instead of going straight, when it's going at an angle like theta there, then the m is the number of bands. This was the first band. So the m would be 1. The wavelength is the wavelength between the wave fronts. And a is the slit width. We're going to use this formula to do some calculations a little later. We did mention it last week. If you look at past exam papers, a lot of calculations require this calculation. Okay, guys, I think that's enough for the moment. Let's go to a short break. Remember to carry on posting on the page, get your answers in, and make sure that you're following with the notes. You can download the notes for this evening's session from www.learnextra.co.za/live. We'll see you directly after this break. Welcome back, guys. Great to be with you. I hope you're following. I love seeing the posts on the page. I will try and get to some of those after the show. So please carry on posting. We will get your answers. Remember, if you have a particular question, you're not getting answers, email us, helpdesk@learnextra.co.za, and I'll make sure you get an answer, particularly from this evening's show. Okay, so guys, what we've been dealing with is interference, the concept of constructive and destructive interference, and we've looked at how we can use interference to explain single slit interference, the diffraction, single slit diffraction. The pattern that we saw is a diffraction pattern, and we give the reason why it's happening as interference. Make sure you've got that very clear. Now, why is this important? Well, I'm sure you've read and you've heard about people saying, is light a wave or is it a particle? Well, one of the thoughts right way back was that light has to be a wave. The reason that people were saying light has to be a wave was because of evidence from an experiment. Now, even great minds, somebody like Newton, said, you know what, I think light is a particle. But when we come to look at diffraction through a single slit or interference through a double slit, particles, if they travel through single slits or even through double slits, they're never going to interfere. The interference is not something particles can do. You can't take two particles, bounce them into each other, make a bigger particle, they separate and make smaller particles again. Doesn't happen. Not in this universe, or as far as we know. So we need to understand that light, based on today's lesson and the evidence that I'm presenting with you, certainly, definitely has a wave nature. Next week, we're going to be looking at the photoelectric effect. And there's evidence that light has a particle nature. And so we'll resolve that by saying light has a dual nature. It has both a wave nature and a particle nature. But at the time that Young did his experiment, he didn't know about the photoelectric effect. And so he was looking for evidence to show that light is a wave. Let's look at the experiment and let's describe it for you. So the first thing that we see, it's very similar to the single slit diffraction. What we recognize is that we have over here some wave fronts. So these are wave fronts. And we've got a barrier, and there are two slits. Notice they are separated by a small little separation, but there are two slits. The wave fronts are a certain wavelength apart, lambda, and they're moving towards the screen. Now, what you need to recognize with Young's experiment is that there was constructive and destructive interference here because we've got two coherent sources. You can see these if you look at a ripple tank with waves. Now, I wanted to show that to you, and of course, the place to look for it is on PHET. If you Google PHET, there's a simulation on wave interference there. Unfortunately, I was trying to load it and it keeps on bombing out, so I can't show it to you this evening. I'm very sorry about that, because it would have made it very much clearer how water waves interfere, the pattern water waves undergo, and then we'd be able to look at Young's single slit experiment as well as Young's double slit and the single slit diffraction pattern, be able to see it as a simulation. But I really suggest you get hold of it as a Java download, and you should be able to see it on most smartphones and even on a computer. It doesn't take a lot of time to get it down. Right, let's see what the differences are now between Young's experiment, the single and the single slit diffraction pattern that we saw earlier. The explanation is exactly the same, but here is the important difference. What we should recognize is that when you've got a double slit like this, notice something. The bands are not one big and one small, but they're evenly spread. They're more or less of the same nature, and they tend to be about the same brightness. The ones on the edges will get a little bit dimmer. The reason that we're saying this is happening is at this point, where the red band is, there is constructive interference. And the black band or the dark band, this one is known as destructive interference. Now, you won't be asked to do calculations for a double slit, but you will be asked to interpret them, just like we had in the previous question. So let's go right back to that question that I gave you, and let's see if we can get some answers. So here's the question, and let's see if we can work through it in the time. Notice we were first of all asked to find what was happening at point A, where we had two troughs overlapping. So we had a trough, and where we get a trough meeting a trough, what's going to happen? Guys, don't get confused now. They're both going down. They're in a trough. They meet together. They overlap. You're going to get constructive interference here. So the trough is going to get bigger. One trough, another trough, the trough is going to get bigger. If it was a crest meeting a crest, what would it be? Also constructive interference. So when are you going to get destructive interference? Let's look at it on the diagram. Where you're going to get destructive interference is in that position there, where a crest meets a trough. Notice my blue line, this blue line, is meeting the dotted line. And when that happens, that point there is going to be destructive. What's interesting is that if you look at water waves like this, all the points of constructive interference line up and they form a line, and all the points of destructive interference form a pathway as well. So in water, you'll get a passage where there's no waves forming, and there's a passage where there are bigger waves forming than there were before. We call these nodal and antinodal lines. The nodal lines are where there's been destructive interference, and where there's constructive interference are antinodal lines. So make sure you understand that and you've got that very clear. So let's have a look now. The next thing is to say, what about position P? Is it a dark band? Remember, a dark band will be destructive, or a red band, which will be constructive. So let's have a look at it. And let's pick it out. We're wanting point P. Over here is point P. Now, we haven't got the full range of what's happening, but we've got these lines that are joining up. And if you look at that point, which is on the line representing P, where this one is a line representing Q, this one is a line representing R. We go back to each of those lines. As I mentioned to you, that one is destructive, So P must be destructive. If it's destructive, it's going to be a dark band. Whereas Q is going to be a red line, and R, because of the pattern, is going to be dark. And that's exactly what we'd expect. It's going to have a central band, which is red, 2 fringes on the side, which are dark, then red, then dark, and so on, just like we've explained. So make sure you understand the reason for that is because the distance to those positions are, if they're constructive, they're a whole wavelength apart, where one is a whole wavelength and the other's different by half a wavelength or more, there's going to be destructive interference. Okay, got that. Right, I want to move on now to our last question, and hope we can fit it in, because this is on single slit diffraction. Let's make sure that we get this right. Again, we're told we've got monochromatic light of wavelength, and they give you the wavelength 410 nanometers. Nanometers, we must convert to meters. Don't get this wrong. Nano, how do we convert to meters? Immediately I see it, I want to do the conversion. And nano is times 10 to the minus 9. So remember, micro with a symbol like that times 10 to the minus 6. Nano with the N is times 10 to the minus 9. So we convert it like that. It tells us is passed through a single slit at a fixed distance from a screen. The angles at which the first minimum, alpha, and the second minimum, beta, occur are measured. Okay, so let's have a look at the picture, because we can learn a lot from diagrams and reinforce what we've learned in our studies by looking at the diagrams from exam papers. So there we've got the slit width is A. We know that this is alpha, first minimum. This is the midpoint of the central band. And that's where we always measure the angle from. So from the middle of the slit to the middle of the light band, that's the straight line distance. That's the middle of the central band. What we're measuring is the angle alpha, in blue here, is to the first minimum. Minimum means that there's been destructive interference, means it's a dark band. The second minimum will also be a dark band. Minimum, meaning between these, is going to be a slightly bright band, but we're only worried about the dark bands when we're looking at the calculations. So please remember, when you see minimum, it's dark band. When you're doing this calculation, you're going to look at the light and dark bands. So first minimum, we're dealing with the angle alpha. Second minimum, we're dealing with the angle beta. And I'll just show that to you in color and do it with orange there. So beta is orange. Let me just erase that so we can write it clearly. So you can see that beta is minimum, second, and alpha is the first minimum. Excellent. Moving on. What other information are they giving us? They say the experiment is repeated using the same light, very important, but a slit of different width. So they do the experiment, then they change the width. They're being tricky. Remember, we know the relationship between the angle of diffraction, the wavelength, as well as the slit width. We know that. So what we're going to do is we change the source, we change the width. The results obtained from the two experiments are represented in the table below. So let's look. Slit 1, we're told the angle of the first minimum was 10 degrees. The angle of the second minimum was 20 degrees. The slit 2, the angle is only 5 degrees, and the second minimum is 10 degrees. Okay, so let's be very clear about this. We are going to have to answer these questions, but we need the equation out in front of us. We're going to say the angle theta is equal to m lambda divided by a. Now, what they're asking is which one, slit 1 or slit 2, is the narrower slit. And you've got to explain your answer. Guys, this might look a little confusing. What do we know about the angles? Notice that slit 1 gives us a minimum of 10 degrees, whereas slit 2 is giving us a minimum of 5 degrees. The angle of diffraction has got less. So what we're seeing is here, there's been a decrease in the angle. Decrease of the angle. Now, how are we going to decrease the angle? Notice something. When we're comparing this, we're dealing with m in equal 1 for both of them. We're looking at the first minimum. We haven't changed the wavelength, so the wavelength has been constant and the number has been constant. It could be 1 or it could be 2 because we see the same pattern. There's a decrease. If we keep the numerator the same and the angle gets smaller, then what's happened? We know that sine theta and theta are related because for small degrees, we know that sine of the sine graph will look something like that. So when the angle is 0, it's going to be 0. When the angle is 5, the theta value, sine theta, is going to be small as well. So recognize this. What's made sine theta get smaller? What's made the angle get smaller? Well, the only thing that we've changed is that, A. What's happened to A? To make it smaller, we've got to make A bigger. Agree? If you take a look at this. If you've got 10 and you divide it by 5, you'll get an answer of 2. If you take 10 and you divide it by a bigger number, like 12, you'll get an answer of 0, something. I don't know what the answer is. So just make sure that you understand. The A has got bigger, then the answer will get smaller. And that's exactly what we're seeing here. The value got smaller. So what's that saying? Slit width is bigger. This one is bigger. Whereas slit 1 is the narrower one. So to answer our question, we must put down slit 1. It's narrower. Why? Because the angle of diffraction is greater. The angle is bigger. Angle is greater. Okay. And then the last thing that we're asked to do is to do the calculation. And you know what? I'm just going to set it up for you, and I'm going to ask you to substitute in. Pick the data from the table to calculate the angle, to calculate the width of slit 2. So slit 2, we're going to say 5 degrees, substitute 5 degrees in there. We want the angle of that. We know the nanometers there. We know that's 1. We substitute it in, and we'll get the answer. Guys, I'm sorry we didn't finish that, but I hope you can see how to do it. It's been my pleasure being with you. Thanks to Macmillan for making this possible. I've really enjoyed it and hope that you understand now those two very important principles, diffraction and interference. This gives us evidence of the wave nature of light. Next week, we'll be looking at the photoelectric effect, so join us then. Thank you so much for being with me. From me, John, post your questions. I will check Facebook directly after this. Good night. Bye.